Hey everybody, welcome back. We're going to finish up this section here with a few more examples. So last time we were talking about how when you take a sample that's from a population and compute its mean, that's its own random variable and has its own probability distribution, and that will have its own mean and its own standard deviation, which depends on the original population mean, the original standard deviation, and then the n. And the mean of the sampling distribution that remains the same, whereas the standard deviation is quite different. It's much smaller. It's the original standard deviation divided by the square root of n. And this is what we use. We want when we specifically want to compute the probability that a sample mean is in a certain range. So, and we can do this, and we can only do this, of course, if we know ahead of time that the sample means are normally distributed, and we have to check that either the original population is normally distributed or the sample size is at least 30. Okay, now, and of course, a lot of the examples I'm going to give you meets one of those two conditions. Otherwise, we can't really do anything. All right. So last time we did example 1, so let's look at example 2. This is a little more context to it. The scores for males in the reading portion of the SAT in 2016 were normally distributed with a mean of 495 and a standard deviation of 120. A random sample of size 20 was taken. Okay. So right away we know that because the original population is normally distributed, we know that our samples means are normally distributed. The fact we need that because otherwise the sample size is less than 50. So we do need the fact that it's normally the original population is normally distributed to go further. So the mean of the sample means is going to be the same. It's 495, and the standard deviation sigma x bar is 120 divided by the square root of 20. Okay, and that turns out to be 26.833. All right, so if we want to find the probability that a sample mean is greater than 530, okay, so this is the probability that x bar is greater than 530. So this would use normal CDF. Now let's maybe to draw a picture of this. Here's our mean 495. 530 is over here, and we want this region right here. So this will be normal CDF of 530. And take 1000 to be positive infinity. And the mean we said is 495. And the standard deviation is 26.833. And when you compute this, this is 0.096. Okay. Another way of looking at the, well, yeah. Now it's not, we're going to notice that this doesn't say that 9.6% of all the scores are above 530. That is not the case at all. What we're saying is that 99.6% of the sample means would be above this range. Okay, so if our sample size was 20. The probability of a sample mean is between 480 and 500. Okay, well, in that case, we have here's 480, 500. We're talking about this area here. We're talking about the probability that x bar is between 480 and 500. Again, it doesn't really matter if we include the endpoints or not, because this is a normal distribution. So we would use normal CDF 480, 500, 495, and 26.833. And this turns out to be 2.286. Your things will not necessarily be drawn to scale, but that's okay. The probability of the sample mean is less than 460. Well, that'll be this situation. And so the probability that 460 is less than, we'll try again. Probability that X bar is less than 460. We use normal CDF of negative 10,000, 460, 495, and 26.833, and that is 0.096 again. Okay. All right. Another example on page 4, example 3. This is an example, and hopefully there's some nice practical applications of this. We have a machine that fills paint cans, and it's set to fill paint cans with a mean of 128 ounces and a standard deviation of 0.2 ounces. Now, a random sample of 40 cans has a mean of, let's say we take a random sample and get a mean of 127.9. Is this unusual? And if it is unusual, we should probably fix the machine. All right, so let's think about this for a moment. First of all, our n is 40. Our sample size is 40, so we know that the central limit theorem says that the sample means are normally distributed. Our mean, UX bar, should be the mean of the original population, which is 128. So this is 128, and sigma X bar would be 0.2 divided by the square root of 40. Okay. So that turns out to be 0.032. All right. Now, before we go, how do we do this? Now, they don't ask us find the probability that X bar is in a certain range. What they're asking is this unusual? Well, let's just think about this. Here's our sampling distribution, and the mean is 128. Okay. And we get 127.9. Now, you say, oh, well, that's not very different. That's almost 128. But the question is, what's this difference? How many standard deviations are we away from this? Okay. And 0.1, 127.9 minus 128, that's equal to negative 0.1. Well, that's approximately 3 times 0.032. There's 3 standard deviations away. So this is actually way, way, way over here on the curve. Okay, more than 2 standard deviations, probably more than 3. Probably almost exactly 3. And if we were to find out the probability, find what this region is, the probability that X bar is less than 127.9. Obviously, it doesn't make any sense to say what probability that it's equal to that, but the probability that X bar is less than this would be normal. We could compute that as normal CDF of negative 10,000, 127.9, 128, and 0.032. And this turns out to be 0.0009. So yes, it's very unusual. Fix the machine. All right. And this is a kind of a trick. This is a trick we're going to be using when we get, especially when we get into hypothesis testing. We're going to ask: is this sample mean? Is this unusual, or does it fall into an unusual range? The last example: if a population is normally distributed with a mean of 48 and a standard deviation of 6, and a random sample size 10 is taken, which is more likely, that a randomly chosen value being less than 40, or a randomly chosen sample mean, sample having a mean, maybe I should say sample having a mean being less than 40. And hopefully by now you kind of know what the answer is. The sample means are more compact. They're less spread out. So it's going to be more likely that it's being less than 40. It's more likely that a single value will be less than 40 than a sample mean. By the way, the central limit theorem applies because we're given that the population is normally distributed, so we don't really care about what the size of the sample is. And so if we want to take the probability, if we just use normal CDF, so basically here's our situation. Our mean is 48, and 40 is over here. If we're just using our original population, we use normal CDF of negative 10,000. There. 40, 48, and we said the standard deviation is 6. So this represents the probability that a single value is less than 40, and that's 0.0912. Okay. That's probability of a single. That's a single value probability. A single value is less than 40. Now, what would be the other probability? That would be normal CDF of negative 10,000, 40, 48, 6 divided by the square root of 10. Okay, I didn't compute what that is, but that's that standard deviation. And this turns out to be 0.00001. Okay, so this is the probability that a sample mean is less than 40. Almost 0. Alright, so I hope you get the idea here. Go ahead, do the homework, get lots of practice, and we will see you next time.